Alrighty, now the moment we've all been waiting for, the normal model. And this lesson will focus on the basics of a normal model, and then in the next lesson we'll actually talk about using it to find proportions of data. Now, the normal model, contrary to their name, is a very unusual phenomenon which can reveal information about the population. The normal curve is a special type of continuous density curve, and the below image is how we graph the normal distribution. So you'll see this kind of structure, it's symmetric on both sides, and these values right now, again, are like, what do these mean? But you can see I've got mu, and then we have minus 1 sigma plus 1 sigma. Then we have mu plus 2 sigma, mu minus 2 sigma, mu plus 3 sigma, mu minus 3 sigma. So these are a few characteristics we look at when we describe the normal curve. First and foremost, since it's symmetric, we should expect the mean and the median to be equal. But also here, the peak in the data, the mode, is also equal. So all three of these measures of center are equal. The shape appears approximately symmetric or unimodal. The measure of center that we're going to use is going to be the mean, but more specifically mu, which is the population mean. And the spread we'll use is the standard deviation, but again, more specifically sigma, the population standard deviation. Now, mu and sigma are called parameters, and these describe characteristics about the population. This is if you knew the true average income of Houston, Texas. This is the true average height of men in the United States. This is the true average number of cars that US adults will own in their lifetime, etc. So these are true values, and usually we do not know the true values. We only know information about our samples, and we just hope that enough time and enough information would lead us to believe what the truth may or may not be. Now, we use this fancy notation to indicate a normal model. X, which is our variable of choice, we'll have to define it. This little squiggly here means distributed. This capital N stands for normal, and then you'll write in the values of mu and sigma. So these 5 components need to be there. Not x equals n, not x plus n, a little x squiggly n. So in English, this reads as x is distributed normally with the population mean and the population standard deviation. So now let's take a look at our curve here, and this is what we call the empirical rule. Now, this can only be used, and emphasis on only, if the data is normal. The empirical rule does not work for skewed distributions, for bimodal distributions, for uniform distributions. It only works if the data is normal or approximately normal. And here's what it says. So within one standard deviation, you are going to contain 68% of the data. Within 2 standard deviations, you're going to contain 95% of the data. And within 3 standard deviations, you're going to contain 99.7% of the data. So we're going to use this to kind of formulate these different sections here. So I told you one important thing, and that was that in the first section here, this should be 68% of the data. Well, it's 68% of the data wedged in between 2 of these wedges. So if the total is 68, that means each section should be about 64. So I'm going to 68, not 64, 34% here, 34% here, because 34 plus 34 is, you guessed it, 68. Now, in the next section, we have the following, is that there is 95% of the data located within 2 standard deviations of the model. But I already know that there's 68% within 1, so I need to find the difference between 95 and 68, which is about 27. But again, that 27% is split in between the 2 sections, meaning that each of these wings here is really going to be about 13.5%. So let me write those in percents. All right, excellent. And then in our last one here, kind of, sort of. Oh, I think I just drew in it. Whoops. Let me highlight that. In our last section here, we are accounting for 99.7%, but we already know 95, so I'm going to take the difference there, 4.7 divided by 2 sections. This tells me that in the green, or within 3 standard deviations, I'm going to contain 99.7% of the data, but these green sections each account for 2.35% of the data. Now here's the important thing. I've only accounted for 99.7% of the data. We should always give 100%, and that's going to be the same here. The area under the curve is always equal to 1. So each of these sections and even these tails here need to add to 1. So if I have 99.7% of the data, I have these two tails over here. So this tails, and these tails just go to infinity. I don't know those last numbers. They could be anything, but the fact of the matter is it's going to be a very extreme value that is just not worth mentioning. And we mentioned these types of unusual features back in the first half of this unit, and those are called outliers. So an outlier for a normal curve is any observation above 3 sigmas or below -3 sigmas. And so of course there is 0.3 in the data there, so that means this is going to be 0.15% and this is going to be 0.15%. Now when I add up the entirety, I should know about 100% of the population. Again, this is all theoretical. You're never going to know 100% of the truth, but we can use this empirical rule to approximate these different proportions of data. Now, this is not very common on the FRQ section of the AP exam. It's actually more common on the multiple choice section. But it's going to help us to develop our understanding of where these different observations have their percentiles or their z-score locations and what percentile of the data follows that z-score. So let's take a look at an example here. And this will show up on the multiple choice. You can, of course, find the answers using the normal model, but understanding the empirical rule is significantly important for your understanding of the normal distribution. So here, at a local restaurant, the amount of time that customers have to wait for their food is normally distributed with mu 26 and standard deviation of 5. Draw a sketch of the curve. So here's what we got to do. First and foremost, we saw this notion here, right? I can say that x is distributed normally with a mu of 26 and 5. Now, that's all fine and dandy, but what is x? And so you have to look at the context of the problem. X is going to be our wait times, more specifically, our customer wait times. And now that I know what x is, I know that this means customer wait times are normally distributed with a population mean of 26 minutes and a standard deviation of 5 minutes. So that's kind of the understanding and reasoning that we go through there. So now let us draw our normal curve. And here we go. So at the mean is going to be 26. I'm going to go 1 up, 1 below. So 1 up will be 31. 1 below will be 21. If I go 2 above, so 31 plus 5 is 36, but this is the same thing as 26 plus 2 sigma, 26 plus 2 times 5. And here, 26 minus 2 times 5. All right, so now let's go 3 sigmas out, 11 and 41. So then anything not within that 99.7% of the data is going to be considered an outlier. So if you have a wait time less than 11 minutes or a wait time greater than 41 minutes, we're going to look at you a little funny because that's kind of unusual. All right, so now that we have these sections, you don't need to draw them in, but what helps me is just the visual here of like, okay, here's all of the different sections. And these are going to hold true anytime you have a normal curve. So I'm just going to draw this in. So 34, 34, 13.5, yada, yada. So understanding that is just going to help me each time. Alrighty, so what happens now is we are going to use our curve to find the following proportions, or specifically here, percentages. What percentage of customers have to wait between 21 and 31 minutes? So what percentage, all right, between 21 and 31? Well, if I look at the data there, I went 1 up, 1 below. What percentage of data occurs within 1 standard deviation? Well, that's going to be 68% of the data, and that's going to be by the empirical rule. Okay. What percentage of customers wait less than 11 or greater than 41? Oh, we just talked about this, right? Anything above 3 sigmas or below 3 sigmas is what we consider an outlier. So I'm going to highlight that in red because that's kind of unusual. That's our danger zone there. Well, we know that our model, empirical rule, accounts for up to 99.7% of the data. So we know that 100% minus 99.7% will give us 0.3%. And again, this is also by the empirical rule. So again, it's not very common to see this like on the free response section. It might show up in the, at least the reasoning behind it, show up in the multiple choice, but we're just going to do some Delta math practice on this just because it's not heavily tested on the AP exam. Now, thankfully the empirical rule is useful. However, not all observations of a distribution of a variable of interest fall at these specific locations. In fact, we need to standardize our distribution in order to find the proportion, or the area, of data located within a certain interval. So when we standardize z-score, we are going to use, and quite literally in the name, the standard normal curve. And this happens where mu is 0 and sigma is 1. And this just helps us because on our AP exam tables, we typically, right, I've been mentioning this idea that 99.7% of the data falls within 3 sigmas. So I'm literally looking, each distribution is going to be different, but when I standardize it, it's going to fall at these specific z-score values. So we produce the following normal curve. So this is just saying that x is distributed normally with a mu of 0 and a sigma of 1. Now this will be the same thing when we put in the data. So now we said x customer wait times is normally distributed with 26, mu 26, and sigma 5. So let's look here. 26, 31, 36, 41, 21, 16, 11. So there's two numbers here, right? The number in the blue was our customer wait time distribution, and the number in the red is the standard normal curve. So how are they related to one another? Well, let's do a little math here. I know everyone's favorite. Let's take the z-score at 31. So I'm going to do 31 minus the mean of 26 over 5. Well, 5 over 5 gives me 1. So notice that at 31, it has a z-score of 1. Okay, well what if, let's go negative. Let's do 16. So 16 minus 26 over 5. It's going to give me a z-score of negative 2. And notice 16 happens here at negative 2. So this is how we read it. Blue is a specific information about the distribution. The red, or the standard curve, is that location from the mean, meaning that a wait time of 31 minutes falls 1 standard deviation above the mean. A wait time of 16 minutes falls 2 standard deviations below the mean. So I have my actual observation, and then the standard normal curve there is going to allow me the opportunity to say how far away from the mean we are. Are we above the mean? Are we below the mean? So whenever we fill in these normal curves, I just want you to get into the practice of filling in the standard normal curve and then filling in the distribution, because this is going to help us to find the z-scores and then consequently the percentiles. So that's just an overview of the empirical rule, the normal model. In the next and final lesson of this little Unit 1B series, we're going to use the normal distribution to actually calculate data percentiles. So stay tuned for some very exciting calculations. I don't know why I did that, I'm so sorry. But anyway, stay tuned for our last lesson of Unit 1B.